Alright, welcome. This is the Webster Grove School District 8th grade science, chemistry, goal 4 video notes. Alright, so um, to start off, the goal is that students will be able to describe how volume and state of matter changes in response to increase or decrease in energy. Okay, so if you're achieving at a level 3, you're doing exactly that. You are able to describe how volume and state of matter changes with an increase or decrease in energy. That's the other important part of this goal. If you are above meeting the expectation, you are also able to explain how a change in energy affects the density of matter. Alright, so here we go. The kinetic molecular theory. We broke this down in our last notes, but for a review, kinetic means moving. Okay? And molecular, we have molecules. In theory, we have idea. Okay? So this is the idea of moving molecules. Alright, so in our last goal, we knocked out these two parts. All atoms and molecules are in motion. Yes, they are. We know that. And the motion of these atoms and molecules is random. We don't know whether they're going to be from 1 second to the next. For this goal, we're going to look at these three parts. The motion of the molecules is dependent upon temperature. That's a really important part of this goal. Second part, the higher the average temperature, the faster the motion, and the lower the temperature, the slower the motion. Okay, so we have to concentrate on speed of motion here, but we also have to concentrate on how loosely those molecules are moving together. Okay, and how easily they're flowing over each other. Okay, the last part is a change in motion of atoms and molecules will occur with changes in temperature. So that means like they're able to pass loosely over each other, or they're right up close next to each other and they can't pass over each other at all. Okay, so these are the three parts of the kinetic molecular theory that we will be looking at in this goal. What in the world is this? Okay, don't freak out. Let's figure it out. Okay, on our y-axis here, we have temperature. And this is increasing temperature. On our x-axis, we have heat, or we could also say energy. Okay, let's say energy for the sake of this argument. So energy added, temperature added. Okay, so what we have here, we have matter starting off as a solid. When energy and temperature increase, that solid meets the freezing and melting point. Okay, that's right here. So it could be a solid, it could be a liquid at this point. For water, we know that it's 32 degrees. So as more energy and as more temperature is added, it reaches the liquid stage, liquid state of matter. That's this right here. And then it reaches this condensation or vaporization point. So condensation, that is the gas turning back into a liquid. Vaporization, it's that liquid turning into a gas. Okay, so more temperature, more heat is added, that liquid turns into a gas, and then right at the point where it is totally vapor, it is a gas. And the reverse is true also. Okay, with less energy, that gas becomes a liquid. It condensates. We learned about that last year in the water cycle. And with less energy and less temperature, that liquid freezes and becomes a solid. Okay, so that's how this chart works. Be able to read and understand this chart. Read and understand. Okay, if you have questions about this, ask that for your last question. Alright, let's look at this. This is a phase change diagram. Okay, and for the phase change diagram, there's one of these diagrams for every single piece of matter that we know of, because every single piece of matter could be a solid, could be a liquid, or could be a gas. It really just depends on the pressure or the temperature. Okay, so this is the phase change diagram for carbon dioxide gas. Okay, this is the triple point. At this point, at this pressure, and at this temperature, it could be a solid, a liquid, or a gas, depending on small changes in temperature or small changes in pressure. Okay? So this is just to emphasize that any matter could be a solid, a liquid, or a gas, depending on the pressure and the temperature. Okay? Solid carbon dioxide is dry ice. Liquid carbon dioxide we don't see much, but when we see that solid carbon dioxide going from solid to gas, that's that gas that we see coming off of dry ice. That's the vapor. Okay, so it kind of skips over that because we don't have this really intense pressure. We just have quick changes from super cold to pretty warm. Okay, so that change just breaks it down from a solid to a gas, and we'll see that later. Okay. All right, in this diagram, we're going to talk about what happens with energy, temperature, and volume as matter goes from a solid to a liquid to a gas and back again. Okay, so starting off with a solid, we are increasing our energy. And yes, you need to draw these arrows. Okay, and we are also increasing our temperature. And we are increasing the amount of space that the matter takes up because the molecules are getting further apart. And that solid is becoming a liquid. And we call this the melting point. Okay. And that is a different temperature or different pressure for all different types of matter. For water, we know it's 0 degrees Celsius or 32 degrees Fahrenheit. Okay, so then as we go from a liquid to a gas, we again have an increase in energy. And that increase in energy means an increase in temperature. And the molecules are again spreading further apart. And it becomes a gas, and that's vaporization. Okay. So all things can become vapor, and it becomes a gas. Okay. So then, as in the reverse, gas can become a liquid, and when that happens, the particles get closer together, and volume is decreasing. Volume is going down because the particles are getting closer together. They're not as loose as they once were as a gas. Okay, so they're becoming closer together, and that means that temperature is decreasing. Okay, we see this happen when water vapor hits the side of an ice cold glass of water. It condensates. And so that condensation on the outside of the glass, that's what's happening. The air is being cooled around it, and so the water molecules come out of the air and become back into a liquid. Energy is decreasing because temperature is decreasing. We call this condensation. Okay? So it's a liquid. Liquid can then be continually cooled. And what happens here is that it becomes a solid. So again, it's taking up less space because those particles are getting closer and closer and closer together. They're not as freely moving anymore. They're more They're getting close to the vibrating stage. Temperature is decreasing, and because temperature is decreasing, energy is decreasing. We call this the freezing point. Okay, so there's that. Moving on. What happens?
Since balloons don't have engines, they need to be lighter than air to fly. We tend to think of air as weightless, but the molecules of oxygen and nitrogen in the air actually do have weight. A cubic foot of air weighs about an ounce. If you heat the air inside a balloon, the molecule...
Alright, what happens to density when heat energy is added? Sorry for the technical difficulties. So we can prove this mathematically, and we can also look at a picture or look at hot air balloons and prove it. Okay, so let's say, just for ease of numbers sake, our mass is 4. Okay, 4 grams, and our volume is 2. We'll say 2 milliliters. Okay, so we know that density is mass divided by volume. That's why I did that. Okay, and so 4 divided by 2, we have a density of 2 grams over milliliters. Now, what happens to density when heat energy is added? Well, if we flip back, okay, we would be able to see that when heat energy is added, that means that the volume is increasing. Okay, so volume is increasing. Remember that. So volume is increasing. Let's say we still have 4 grams, but our volume is now increased to 4 milliliters. It's taking up more space. So now our density is 1 gram over milliliter. Our density is decreased. So density decreases when heat energy is added. Density decreases. Okay, when heat energy is added. To have an example of that, let's take a look at hot air balloons.
engines, they need to be lighter than air to fly. We tend to think of air as weightless, but the molecules of oxygen and nitrogen in the air actually do have weight. A cubic foot of air weighs about an ounce. If you heat the air inside a balloon, the molecules move faster and spread farther apart. That means that there are fewer molecules inside the balloon, so it's lighter than the air outside. Each cubic foot of hot air is maybe 7 grams lighter than cold air. That's why balloons are so huge. To lift 1,000 pounds, a balloon needs to be about 65,000 cubic feet. In order to keep the molecules far apart, propane burners keep the air hot as the balloon rises. The only way to steer a balloon is to use the wind. The wind's direction changes between altitudes, so you move up and down to go left and right. When you want to go up, you provide more heat. When you want to go down, you open a hatch in the side of the balloon that releases hot air. You can't really tell exactly where you're going to land. That's why most pilots have co-pilots on the ground to follow them. So that's how a hot air balloon works. I'm Marshall Brain, and that's how stuff works.
Alright, so that video shows us that when energy or when heat is added to matter, it becomes less dense. Particles spread further apart, they're moving faster, they're moving more freely, and so that is what happens to matter when temperature or heat is added. Alright, that's it and that's all for this video. Thanks for watching. Please ask a question at the end and bring that question with you to class tomorrow. Later.